I would like to start the session with William Hall Thurston quotes. Mathematics is not only about numbers, equations, computations, or algorithms. It's only about understanding. Good afternoon, one and all present here. We are in the sixth section of the day three of the international webinar on recent trends in pure and applied mathematics. Presentation tools force you to think through information linearly, and you really need to start by thinking of the whole instead of the individual lines. This presentation session is handed over to Dr. S. Balamurugan, Research Supervisor, Government Arts College, Nellore, Madurai.
Good evening to one and all present here. I am M. Angaleshwari, Research Scholar, Department of Mathematics, Government Arts College, Nellore, guided by Dr. S. Balamurugan, Government Arts College, Nellore. Today I am going to present my paper on equality of total domination and chromatic total domination in graphs. My outline of the presentation is Introduction, Total Domination, Chromatic Total Dominating Set, Equality of Sets, and References. First, introduction. Let G be a simple finite anti-vector graph without isolated vectors. A subset D of E is said to be a dominating set if every D minus D that exists a U and a D such that U and B are adjacent. The minimum cardinality of a dominating set G is called as domination number, and it is denoted by gamma of G. D is a minimal dominating set of a graph G if no proper subset of D is a dominating set. D is said to be a total dominating set if induced subgraph has no isolated vertices. The minimum cardinality of total dominating set of G is called as total domination number, and it is denoted by gamma of D. Next, the definition about chromatic total domination. The subset D of V is said to be chromatic total domination if D is a total dominating set and chi of induced D equal to chi of G. The minimum cardinality of chromatic total domination number is denoted by gamma CHG of G. In any graph, every chromatic total domination set is a total domination set, but converse is not true. In some graph, every gamma T set is a chromatic total dominating set. In some graph, some gamma T set is a chromatic total dominating set, and some gamma T set is not a chromatic total dominating set. While in some graphs, no gamma T set is a not chromatic total dominating set. This observation motivates us to classify all the graphs into three categories. Before entering into equality of sets, we need to know the definition about total domination and chromatic total domination set. Total domination set. A dominating set D is said to be total dominating set if induced D has no isolated vertices. The minimum cardinality of total dominating set is total domination number, and which is denoted by gamma T of G. And what is chromatic total dominating set? A set D is said to be chromatic total dominating set if D is a total dominating set and induced and chi of D equal to chi of G. The minimum cardinality of chromatic total dominating set is called as chromatic total domination number, and it is denoted by gamma CHG of G. Now we are going to see the equality between the total domination set and chromatic total dominating set. Example of chromatic total dominating set. Here the dominating set D equal to total dominating set D is V2, V3, V4, and chi of D and chi of G equal to 3. Hence D is a chromatic total dominating set of G. Now we are going to see the definitions about equality of sets and their theorems. First definition. The equality of sets is divided into three definitions. The first definition is the graph G is said to be in gamma T equivalent to gamma CHG class if every total dominating set is a chromatic total dominating set. Example, let us consider a bipartite graph Km, N. Here, the total dominating set is every two vertices in the upper vertices in the upper set and the downer set, and all these will be in chromatic total dominating set since chi of induced D equal to chi of G equal to 2. These are all the total dominating set, and these sets are total dominating sets as well as total chromatic dominating set. Second definition is a graph G is said to be in total dominating set approximately total chromatic dominating set if some total dominating set is a chromatic dominating set and some total dominating set is not a chromatic total dominating set. Example, in this graph, V1, V2, V3, V4 is a set and another total dominating set is V1, V3, V5, V6. But D1 and D2 both are total dominating set. But D1 is a chromatic total dominating set where D2 is not a chromatic total dominating set. And third Third class, a graph G is said to be in GAM. Total dominating set not equal to chromatic total dominating set if no total dominating set is a chromatic total dominating set. In this example K5, any vertex will be a total dominating set. All these sets is a total dominating set, but all these are not chromatic total dominating set since chi of induced D equal to chi of G equal to N. And by using these three definitions, we have find out certain theorems and observations. The first observation is let G be a chi-critical graph with the cardinality of V of G greater than 1. Then G is in gamma T of G not equal to gamma CHT of G class. Since for such a graph, gamma T of G less than N and gamma CHT of G equal to N. For example, complete graph. And the next theorem is we have found out certain standard graphs belongs to what are the classes we have defined. First, let G equal to Kn where n greater than or equal to 2. Then G is in gamma T not equal to gamma CHT class where total domination number differs from chromatic total domination number. Let G equal to star graph, then G is in gamma T equal to gamma CHT class. Then G equal to fan graph with n greater than or equal to 3. Then G is in gamma T not equal to gamma CHT of class. Let G equal to let G equal to Wn, then G is in total domination not equal to chromatic total domination class. Let G be in complete binary tree, then G is in gamma T equal to gamma CHT class. Let G equal to complete bipartite graph, then G is in gamma T equal to gamma chromatic total domination class. Let G equal to Pn, then G is in gamma T equal to gamma CHT class. Let G be in cycle graph, then G is in gamma T of G not equal to gamma CHT of class if and only if n is odd. And Cn is of E, when n is even, the cycle will be present in gamma T equal to gamma CHT class. The next theorem is let T be a tree if there exist a support vertices U and V such that the distance of Ui equal to 2 for all Ui, the degree of Ui equal to 2 for all Ui and the path joining U and V and distance between U of V congruent to 0 mod 3, then U and V belongs to every chromatic total domination set of T. This gives rise to the another. With the help of this theorem, we have found out the theorem. Let P be the set of all pendant vertices of a tree T. If T has two vertices U, V such that cardinality of n of U intersection P greater than or equal to 2 and cardinality of n of V intersection P greater than or equal to 2 and U, V, P, D, H belongs to E of T, then T belongs to gamma T equivalent to gamma CHT class. The next theorem is let P be a tree in which D of U, V congruent to 0 mod 3 for some support vertices and degree of Ui equal to 2 for all Ui on the path joining U and V. If there exists a support vertices W such that VW belongs to the X set of T and either n of W intersection P greater than or equal to 2 or for some support vertex X, distance between D of W, X congruent to 0 mod 3 and degree of Xi equal to 2 for all vertices Si on the path joining W and X, then T belongs to gamma T equivalent to gamma CHT class. Now let us take let D be in caterpillar, T is in gamma T equivalent to gamma CHT class if and only if T has two support vertices U and V satisfying one of the following properties. The first one is cardinality of n of U intersection P greater than or equal to 2, cardinality of n of V intersection P greater than or equal to 2 and the edge UV belongs to edge set of T. If D of U, V congruent to 0 mod 3 and distance degree of Ui equal to 2 for all Ui and the path joining U and V, there exists a support vertex W such that VW belongs to the H set and cardinality of n of W intersection P greater than or equal to 2 or first some support vertex X, D of W, X congruent to 0 mod 3 and degree of Xi equal to 2 for all vertices on the path joining W and X. And these are the theorems which we have given under the equality of sets. And the references of the above theorems. Thank you.
No questions? Okay, very nice presentation.
Thank you, sir.
I congratulate to Mr. Angali, sorry. Thank you. Next candidate. I think she may be submit on coming July. She has completed his research work. But I think many more results pending in this area. In particularly, changing and unchanging properties of a chromatic total dominating set as well as a chromatic weak dominating set also. So many more area pending in this research field. So people are doing well. Thank you.
Thank you, ma'am, for your presentation. Next, I invite Ms. M.J. Abhishek for her presentation.
I am M.J. Abhishek, Research Scholar, Department of Mathematics, St. Jude's College, Totor, under the guidance of K. Rubin Mary ma'am. My topic is Harari Index of LEMMA mean graph. Introduction. Graph theory is the study of various graphs and can be used to model many structures in the real world. Graph theory has experimented a fast development during the last 30 years. Graph theory increasingly find that many of their problems can be solved on their research furthered by the use of computing techniques. The Harari index of a graph G, denoted by H of G, has been introduced independently by Walwick and by Ivanshu in 1993. It has been named in honor of Professor Frank Harari on the occasion of his 70th birthday. The Harari index is defined as follows. H of G equal to summation x comma y belongs to V of G 1 divided by dg of x comma y, where the summation goes over all unordered pairs of vertices G and dg of x comma y denotes the distance of two vertices u and v in the graph. That is the number of edges in the shortest path connecting u and v. In this paper, we investigate Harari index of some standard graphs which admits LEMMA mean graphs. We will provide a brief summary of definitions and other informations which are necessary for our present investigation. Definition. The G be a R, S graph. A function H is called LEMMA mean labeling of G if it is possible to label the vertices B belongs to V with distinct label H of X from 1 to etc. S plus 1 in such a way that when each edge E equal to xy is labeled with H of E equal to flooring H of X cube plus H of Y cube divided by H of X square plus H of Y square, or ceiling H of X cube plus H of Y cube divided by H of X square plus H of Y square. Then the edge labels are distinct. In this case, H is called LEMMA mean labeling of G. Definition. Let G be a LEMMA mean graph with vertex set B of G and edge set E of G. The distance dg of x comma y between two vertices x comma y belongs to V of G is the shortest path in G between x and y. Main theorem. Theorem 2.1. Let friendship graph F1, Fm be a LEMMA mean graph. Then Harari index of Fm is H of G equal to 1 divided by 3n into 1 plus 2m into m minus 1 into 2. Here this is the example is F4. Here we have to find H of G equal to 1 divided by, that is distance between shortest path. First V1, V2, the distance is 1. Then V1, V3, the distance is 1, etc. We have to find for V2m, that is 1 divided by 1, 1 plus 1, 1 plus 1, 1 plus etc. For we have to find for all. Then the final is 1 divided by 12 into 1, 1 12 times, then 2 24 times. We have to generalize for Fn, 1 divided by 3n into 1 plus 2m into m minus 1 into 2. Therefore, H of G equal to 1 divided by, that is 3m. 3m into 1 plus 2m into m minus 1 into 2. Then next theorem, let F3, Fpm be a LEMMA mean graph. The Harari index of F of Pm is H of G equal to 1 divided by summation j equal to 1 to 2 m plus 1 into j plus m into 3 plus summation k equal to 2 to m minus 1 summation j equal to 4 to m minus k into j. Here the example is f of p7. This also we have to prove by that method. The next theorem, let by star b m comma m be a LEMMA mean graph. Then Harari index of b m comma m is H of G equal to 1 divided by 2m plus 1 into 1 plus m into m plus 1 into 2 plus m square into 3. This is the example. Then theorem 2.7, let y3, ym plus 1 be a lemma mean graph. Then Harari index of ym plus 1 is h of g equal to 1 divided by summation j equal to 1 to 2 m plus 1 into j plus summation k equal to 1 to m minus 1 summation j equal to 3 to m minus k into j. That is the example. There are some reference. Thank you, sir.
Questions from audience? Abisa,
Yes, sir.
I think already exists Harari index of a friendship graph. Already exists, I know.
Yes.
Harari index of friendship graph is exist, I think. Already, right? Is it correct?
I don't know, sir.
Okay. So what about F tree and the Y tree? You have any definition, or the tree is a Y type, it is called a Y tree, or a tree is a F type, or it is called a F tree? I
No,
think.
sir. Definition is there.
Oh, yes. Okay.
A y tree yn plus 1 is a graph obtained
Okay.
from the path Pn by
Okay.
appending an edge to a vertex of the path Pn adjacent to an end vertex.
Okay. Okay. Any questions from audience? No questions? Thank you, Abhisha. All
Thank
the
you.
best. Okay, thank you.
Sir, thank you.
Thank you. Next person.
Thank you, ma'am, for your presentation. Next, I invite Ms. Jayalalitha for her presentation.
Maria Julie. From Paramedic, from Government Arts College of Paramagudi, I think. Maria Julie? No.
Next, I invite Mr. R. Saktivel for his presentation.
I am Saktivel, Assistant Professor of Mathematics, Chaitammal Arts and Science College, Ramanathapuraam. It is such known for me the set of opportunity present paper in this occasion. My paper presentation topic is intrinsic LPC soft ideal over semiring. Abstract is consists of ideal of intrinsic LPC soft ideal of a ring alpha comma beta cuts of intrinsic LPC soft ideal relation between the intrinsic LPC soft semi-ideal and intrinsic LPC soft semi-ring homomorphism. The investigating their interesting properties. My topic key words intrinsic fuzzy set, intrinsic LPC set, intrinsic LPC soft semi-ideal, intrinsic LPC soft ideal. The definition of soft set it means that approximate value in the fuzzy language. Definition 1, let U be an initial universal set and E be a set of parameters. Let B of U denoted the power set of U and A subset of E, a subset notation, a pair of F comma A is called a subset over U, where F is mapping given by F from A to power set of U. U means universal set. In other words, a subset over U is a parameterized family of subset of a universal set. Definition 2, let U be an initial universal E be a set of parameter fuzzy soft notation F plus U denoted by the fuzzy power set of U. Next definition. The main definition of fuzzy is, it means an intentionalistic fuzzy set A. It is clear that intentionalistic fuzzy set, one membership is mu, another membership is gamma. It is definition as an intentionalistic fuzzy set capital A is a non-empty set X can be defined as follows. A member of X, comma, mu of AX, gamma AX, where mu of AX is X from 0 to 1 and gamma AX 0 to 1. The property of 0 less than or equal to mu of AX plus gamma of AX less than 1. The value mu of A, degree of membership, gamma of A, degree of non-membership. It is alternate intentionalistic fuzzy soft set. The membership value is mu of f of epsilon x and gamma of f of epsilon x. It is range of mu of f of epsilon x plus gamma of f of epsilon x equal to 1. And then the fuzzy membership union and intersection of two intentionalistic L fuzzy soft set over the universal set U. The product of f of A and g of A is defined to the intentionalistic L fuzzy soft f of composition of G, comma C, where C is equal to A union B and the defined as membership value composition of this function. This function is mu of f of composition G epsilon parameter x is this notation mu of f of epsilon x if epsilon belongs to epsilon x minus a, mu of g epsilon x if epsilon belongs to b minus a. This notation is lattice fuzzy soft. Non-membership the main topic definition is an intentionalistic L fuzzy soft set f of A over a semi-ring S is called a intentionalistic L fuzzy soft semi-ideal over S. The following conditions are satisfied. Mu of f of epsilon x minus y less than or equal to mu of f of epsilon x cap. Cap means lattice f of mu f of epsilon y. Non-membership gamma f of epsilon x minus y less than or equal to gamma f of epsilon x cup gamma epsilon x y. Another one mu f of epsilon x y less than or equal to mu f of epsilon x cup mu f of epsilon y and gamma f epsilon xy less than or equal to gamma f epsilon x cap gamma f of epsilon y for all x and y belongs to S. Two main theorem 1 is let f of A the indeterminacy helps a soft ideal over a semi-ring? Yes. Then f of a and f of a are indeterminacy helps a soft ideal over a semi-ring? Yes. This is inequality of membership and non-membership theorems. Another one theorem is let f of a the indeterminacy helps a soft ideal over semi-ring? Yes. Then f of a is an indeterminacy helps a soft ideal over S if and only if f of epsilon level of r comma t comma a is an ideal soft ideal of S for all r belongs to open interval 0 comma 1, t belongs to closed interval 1 comma 0 and epsilon belongs to A. This is main concept of theorem. And then reference my previous journals, indeterminacy helps solve semi-rings, publication of Southeast Asian Journal of Mathematics and Mathematical Science, Volume 7, 2021. Thank you, sir.
Next, I invite Mr. G. Ramkumar for his presentation.
Can you able to see my presentation, sir? Sir,
Yes, Ramkumar.
can you able to see my presentation, sir?
Yeah, you start.
Oh, okay, sir. Good afternoon, and all. Welcome to my presentation. I'm Ramkumar, a student of Department of Mathematics at Government Arts College in Melur. Today, my topic about application of differential equation in real life. Today my contents are definition, classifications, applications, real life applications, conclusions, and then reference. First, you can see what is a differential equation. Equation contains a derivative of one or more dependent variable with respect to one or more independent variable is said to be a differential equation. For example, we can see a dy by dx is an example for differential equation. You can see there are two types of differential equations. One is ordinary differential equations and second one is partially differential equations. What do we mean ordinary differential equation means? Normally we are differential with respect to dy by dx. I gave an example in at class, you can see. And in partial differential equations, it has two or more independent variables. For example, dou square u by dou x square plus dou square u by dou x square equal to 0. And then I have given a definition for ordinary differential equation. A differential equation is an equation containing an unknown function and its derivatives. It gives containing only, it's not an unknown function, it also a derivative also. And partial differential equation definition was given. And ordinary differential equation means most of them did not know the order of the differential equations. Order of the differential equation means the highest derivative is given in this equation. We can see the first derivative dy by dx equal to 2x plus 3. In this derivative, which is the order? Yes, it is the order is 1. And second one we can see highest derivative of order is 2. And the third one we can say highest derivative of is 3. So likewise we can see the order of the differential equation. And then degree. Degree means the highest order of the derivative term is the power. Okay. And now we can see the example d square y by dx square plus 3 dy by dx plus ay equal to 0. In this equation, what is the degree? In definition, you have seen the highest order derivative term. Highest order derivative term is d square y by dx square. In the derivative, a degree is 1. Likewise, other equations similarly. A linear differential equation means it should be in a quadratic.
Sorry to disturb. We can't see the screen, sir. The screen is not visible.
Wait a moment.
Okay, sir. Thank you.
Ramkumar, you have PPT?
Yes, sir.
Okay, okay.
Now you can see us, sir. Sir,
Yes, Ramkumar?
now you can be able to visible my.
No.
It's,
Okay, pa. Ramkumar.
sir.
Okay, da.
Okay, sir. So
Yes,
now
yes.
applications. In applications in differential equations are creating software, constraints, logic, programming, creating the games and assets of algorithms, mother language, boards, artificial intelligence, networking, and the theory and explanations. These are the applications I am going to explain in that work. First, we can see the software. A computer can be extremely variable tools in the study of differential equations. In a in the computer or laptops, we can see many tools. In the tools, we can see a study of the differential equations. I have shown this picture. In this picture, we can see the differential equation tools in computer. In software packages, we are applying the differential equations and wide varieties of mathematical operations in this software package. And also, we are the differential equations to understand the computer hardware belongs to applied physics or electric energy engineering. And constraint logic programming is a form of the constraint programming in which logic programming is extended to include concept from constraint satisfactions. In logic programming also, we are applying the differential, it's a partially differential equations we are applying in the logical programming. And then games, we are playing games. In the games, a differential equation used for modeling the velocity of the characters. And for graphics and visuals also is applied the differential equation. And in mother language, it describes the nature of the physical universes using this differential equation. And then robotic. In robotic, partial differential equation, ordinary differential equations are helped to provide the shapes and interior and exterior designs of the machines. And artificial intelligence, they are used MR images to demonstrate that 10-plex film image generated using the sensitive encoding Gaussian Carlin smoothens. It also is used applied in a differential equation. And also in networking, in music, we are hearing wherever we hear the music. In that music also is applied in different partial differential equations. How partial differential is applied in this music means I have shown in this slide. You can see this equation. And in economics also to calculating the GDP, gross domestic product. For calculating gross domestic product, we are using the differential equation here also. And normally we can see dx by dt equal to gx. After differential, we can see x equal to x naught e power gt. And here x naught is the initial gross domestic product. And in macroeconomic, we can calculate the differential equation by the Popper-Planck equations and why some countries are poorer than other. Also, we have calculated using unequal wealth distributions. And then we have studied about the Newton's law of cooling. Newton's law of cooling equal to d theta by dt equal to minus k d tau minus theta s. Here, theta s means a temperature of cooling object at a time. T equal to means a time since a field first reading. Theta s means a temperature of surrounding media. K means constant. And we are sitting in one type of temperature inside the room, and surrounding we have some type of temperatures. Using this Newton law of cooling and the differential equation, we can calculate what type of temperature we have surrounding us. And radio decay. Radio decay, we have seen a rate of decay of the radio substance at time. T is proportional to mass x of t of the substance left at a time. For example, alpha, beta, gamma. We have three types of rays. And three types of rays also depend on the radioactive substance. In the radioactive substance, it's also applied a differential equation. How it is applied, sir? For example, the radioactive substance equation is dN by dt equal to minus lambda n. Now we have differentiating this equations. We can see n of t equal to n naught e power minus lambda t. I not mentioned this equation in this PDF. And then we have studied the physical laws, Gauss law in electrostatic, magnetic, gravity, continuity equations, dynamics. These and also we have applied the differential equations. And second law also. I am still waiting for this day. I will actually use these equations in my real life. Thank you, sir.
Thank you, Rajkumar. Ramkumar.
Sir,
Any questions?
This is my first presentation, sir. In my life.
Okay. Any questions from audience?
No, sir. Nothing, sir.
No questions, right?
Sir. Thank you, sir.
He is studying first semester student in our college. Recently, he passed the examination of statistical exam. I think is correct, Ramkumar? Statistical exam conducted by the government, Tamil Nadu of the government, right? I think he got 380 marks out of 500. All the best, Ramkumar. Thank you, sir.
Thank you, sir. Thank you,
Okay,
sir.
thank you. Next candidate. Maria Julie.
Miss J. Maria Julie for the presentation.
Okay.
Very good afternoon to all, sir. My voice is audible to everyone, sir.
You have PPT.
Yes, I have, sir.
Okay.
Very good afternoon to everyone. My name is Maria Julie. I am a research scholar of Department of Mathematics, Government Arts College, Paramagudi. Under the guidance of Dr. A. Arivalagan, head of the Department of Mathematics, Government Arts College, Paramagudi. My topic is optimal layout of embedding complete Josephus cubes into extended rooted theta mesh. My outlines are introduction, preliminaries, main results, and references. First, we enter into the introduction. In the past 2 decades, there has been a rapid technological progress resulting in the demand for super-fast computers with the ability to perform concurrent computations and deliver the expected result almost instantly. Next is, all the above functions can be resolved through parallel computers also, and an interconnection network can be designed by a graph which requires processes and links. The processes are denoted as vertices and the links are denoted as edges of a graph respectively. Thus, the problem of efficiently implementing a parallel algorithm developed for one network into the another network, which means a graph embedding problem requires two graphs, that is, two networks. From one network into another network can be designed as a graph embedding problem. So next we move on to the wire length or layout problem. So the uses of wire length or layout problem, which gives means the minimum time delay overall possible mappings from one network into the another network. So the layout or the wire length which emerges from VLSI designs. It's nothing but very large scale integration designs and data structures, data representations, biological models that deal with cloning, networks for parallel computer systems, and structural engineering. And some more also, that is graph drawing, coding theory, and parallel processing systems also. And next, we move on to the preliminaries. So graph embedding. What is a graph embedding? Which means a graph embedding requires two graphs, which needs two graphs. The one is a guess graph, and the another one is a host graph. Guess graph is denoted as G, and host graph is denoted as H. Where the first point is we discuss about the vertices in the guess graph and the host graph, which is F is an one-to-one map from V of G to V of H, which is nothing but the number of vertices in G and H, which means guess graph and the host graph, the number of vertices should be equal in both graphs. And the second main point is discuss about the edge connections. That is, F is an one-to-one map from E of G. That is the edges in guess graph to edges in host graph is nothing but a path. That is P of U comma B. The path should be a shortest path in the host graph. That is F of U and F of for U comma B, which belongs to E of G. Next is the graph embedding, and this is the example of graph embedding, which is we take two graphs. So the first graph is named as guess graph and the second graph is a host graph. So the number of vertices should be equal in both graphs. And here in guess graph, if it is an edge, in host graph it may be an path also. Next is an edge condition. This is the main one for compute the violence problem. So edge condition we denoted as EC. So a graph embedding from a guess graph to host graph is the maximum number of edges of a graph that are embedded on any single edge of H. In mathematical words, we can say that EC is nothing but the edge condition. So edge condition of E is equal to U comma B belongs to E of G, and here it is an edge that is which is a path in P of U comma B, which is in host graph E of H. I used different colors to calculate the edge conditions. So the first one is the edge condition of 0, 1 is 5, and the next is edge condition of 0, 4 is 3, and next is 0, 5 is 3, and 1, 2 is 4, and 2, 3 is 3. Next we move on to the layout or violence. This violence is nothing but the initial step is we need to find out the edge conditions, and the summation of the edge conditions is nothing but the violence, and it should be the minimum value of the guess graph and the host graph. Here we are going to calculate the violence between these two graphs. One is a guess graph and another one is a host graph. So already we have found the edge conditions. So the summation of the edge conditions is nothing but the violence. We need to add all the edge conditions, that is 5 plus 3 plus 3 plus 4 plus 3, which is equal to 18. There are some methods to calculate the violence problem also. The edge isoperimetric problem has two subdivisors. That is, one is the maximum subgraph problem and another one is the minimum cut problem. We discussed about only the maximum subgraph problem, which is used in the violence problem. So the maximum subgraph problem we require two sets, namely as A and B, which we get from a vertices in guess graph, and these two subsets, the number of vertices should be equal. So next we move on to the edges, means modulus of E of G of A is greater than or equal to E of G of B. So here A is an optimal set. Next is move on to the condition lemma. Let G be an R regular graph and F be an embedding of G into H, and the edge cut named as S of H in the host graph. That removal of S leaves into two components named as H1 and H2, and G1 is equal to G of F inverse of H1 and G2 is equal to G of F inverse of H2. And the edge cut that is named as S satisfies the following three conditions. The first condition is for every edge A, B belongs to Gi, I is equal to 1, 2, Pf of A, B is has no edges in the edge cut of in the host graph. And the second one is for every edge A, B belongs to G with A belongs to G1 and the another vertex is in G2, and the path of A, B has exactly one edges in the edge cut of H, that is a host graph. And the third condition is G1 is an optimal set, the edge condition of S is minimum, and edge condition of S is equal to R of E of G1 minus 2 into E of G1. So there are some methods we have to make to compute the violence problem. The first one is the we have to select two graphs and we give a name label to the guest graph and the host graph and propose the embedding. And the second method is the partition of the edge set of host graph and solve the MSP, that is the maximum subgraph problem for V component for vertices. And the third is the establish the proof of correctness of the proposed embedding. And the last step is the compute the optimal variant of the graph embedding problem. Now we are move on to the main results of the variance problem. Here I have selected a complete Josephus cube as my guest graph. So here is the structure I defined as the complete Josephus cube is denoted as CJC, which is n is n dimensional. It is a graph with vertex set is vertex set of complete Josephus cube is equal to V of Qn. This Qn is nothing but a Hilbert cube. So the number of vertices in Hilbert cube and the complete Josephus cube are equal. Labeled with 0 to 1 binary strings and the setup of edges of E of Cj Cn is equal to EH union of Ej union of Ec. This EH is equal to x1, x2 up to xk, xk plus 1 up to xn, x1, x2 up to xk bar, xk plus 1 up to xn. The k runs from 1 to n. And the second one is Ej, x1, x2 up to xn minus 1, xn, x1, x2 up to xn minus 1 bar, xn n bar. And Ec is equal to x1, x2 up to xn, x1 bar, x2 bar and up to xn bar. The edges in EH are referred to as Hamming or Hilbert cube edges or H edges. And the edges in EJ are referred to as Josephus edges or J edges. And the edges in EC are referred to as complementary edges or cross edges or C edges. This is the structure of a three-dimensional of a complete Josephus cube. It has 2 power n vertices and it is a regular graph, that is an n plus 2 regular graph. And the thin lines are represented as H edges, that is Hamming or Hilbert cube edges, and the dashed lines are represented as J edges, that is Josephus edges, and the thick lines are represented as C edges, that is complementary edges. Next we move on to the extended rooted theta mesh. This one I have selected as my first graph. Before knowing about the extended rooted theta mesh, we have to know about the complete binary tree and one rooted complete binary tree. A binary tree is nothing but is said to be a complete binary tree if each internal vertex or parent vertex has exactly 2 children and all the leaves are at the same level. The complete binary tree we can denote it as Tn and which has 2 power n minus 1 vertices. And one rooted complete binary tree is nothing but we obtained from Tn, that is a complete binary tree, and attaching a pendant edge to its root, and the one rooted complete binary tree has 2 power n vertices. Here it is an extended rooted theta mesh is denoted as ERTM and n is required by the dimensional and which is acquired from 2 copies, that is 2 previous dimensional of the complete binary tree. Say RTN that if it is a rooter then RTN power 1 and RTN power 2. By connecting P2 to each vertex of RTN power 1 and the corresponding vertex of RTN power 2 except the root of the pendant edge. Here is an example of the complete binary tree and one rooted complete binary tree and extended rooted theta mesh. And the first figure shows that the complete binary tree which has 2 power n minus 1 vertices, that is the dimensional is 3. So the middle of the graph is one rooted complete binary tree and it has 2 power n vertices. And the last figure shows that the extended rooted theta mesh and next we found the optimal layout of a guest graph into a host graph, that is the complete Josephus cube, that is CJCN into the extended rooted theta mesh, that is ERTM n power n is given by the wire length is 2 power n minus 1 into n minus 3 of n plus 10 minus 2. Next one is the binomial tree. The binomial tree is denoted as Bn the height of the binometry is n, is formed by connecting the roots of two previous binomial trees. That is the two previous dimension of the binomial trees. The height is n minus 1 with a new edge and nominating one of these roots to the root of the new tree. This figure shows that the B4, that is the dimensional, 4-dimensional of a binomial tree. And here is an optimality is complete Josephus cube into binomial tree is given by 2 to the power n minus 2 into n square plus 3n plus 4. These are my references. Thank you, sir. Thank you very much.
Thank you. Thank you, Marie. Your title is very entirely different, right?
Yes, sir.
Okay. Any question from audience? I have one question.
Yes,
What is the meaning of guest graph and ghost graph? You have any definition?
nothing but the meaning of the in mathematics, that is nothing but a guest graph is one guest is coming from another home to our home.
Okay.
So we name it as a guest graph. That's all. One who is lives in the home, which is a host graph. That's all. The owner of home is a host graph, and one who is new enter in the home is a guest graph. That's
Okay.
it's a different way, sir. That's all.
Okay. I know. Okay. இப்ப நான் வந்து ரெண்டு கிராஃப் கொடுக்குறேன்னா எனக்கு வேற என்ன கிடைக்கும்? சப்போஸ் எனக்கு ரெண்டு கிராஃப் வந்து ஃபங்க்ஷன் ஆகுது. சப்போஸ் யூ டேக் வந்து ஒன் கெஸ்ட் கிராஃப் அண்ட் அனதர் ஒன் வந்து கோஸ்ட் கிராஃப். ஃபங்க்ஷன் ஃப்ரம் எஃப். அப்படின்னா எனக்கு என்ன ரிசல்ட் கிடைக்குது?
Which we have to check out the one. If it is an one-to-one mapping, the number of vertices in one graph into the another graph should be equal, and the graph is a single edge, which is an two vertices. In the graph, it may be a path also. So here it is the riddle of the what do you say, sir? It is the riddle of the graph.
I think your condition is on the guest graph and ghost graph. On the number of vertices both are same or not?
Yes, sir. Should be equal. The number of the guest graph and the host graph vertices should be equal.
Equal ஆ இருக்கணும்.
ஆமா. Then only we can proceed.
Okay. What is the definition of a complete Joseph's cube?
Complete Josephus cube requires three conditions, sir. That is EH, EJ, and EC. EH is an Hamming or hypercube edges. We already know about the hypercube, sir. So we get all the conditions from the hypercube edges, and the second is the Josephus edges. That is the mu of the complete Josephus cube, sir. And the third one we already know about the EC. That is the edges in the complementary edges.
Okay. But that graph is not complete.
So is sorry, sir.
That graph is not complete, right?
Yes, sir.
Okay. Who is your guide?
Dr. A. Arivalagan, sir.
Okay. Thank you. All the best. Do well.
Thank you so much, sir.
Thank you for all the presenters. Next, I invite Dr. M. Anita, Head Department of Mathematics, to deliver vote of thanks.
Good afternoon to all. First of all, I would like to thank God Almighty to make this webinar as a grand success. On behalf of our department, I take this time to be kind and to say thanks to the management members for arranging this great webinar as a great start. My sincere gratitude to Dr. SYED Amanullah Hamid, Principal, AMMAL Arts and Science College, Ramanathapuram, for supporting us at all time. No one who achieves success does so without acknowledging the help of others. The helping fingers of my success hands are Dr. G. Suresh Singh, Professor, University of Kerala, Trivandrum, Dr. G. Vaidya, Professor, Saurashtra University, Gujarat, Dr. S. Balamurugan, Government Arts College, Melur, Madurai, Dr. Suresh M. HD, Student Welfare, National Institute of Technology, Karnataka, Dr. R. Rama, University of Technology and Applied Sciences, Oman. They are accompanied with all the sessions and make this webinar a grand success. Their responsibility, presentation and clarification are unforgettable moments of this seminar. I also my sincere thanks to Dr. S. Malamurugan for their continuous guidance, encouragement and leadership, who has been the driving force behind this webinar. Thank you, sir. I wish to thank each of you for your participation and presentation in this 3 days journey. Thank you, participants. I would like to thank the teaching and non-teaching staff and students who are all taking part of this webinar for their support, whose preservation and this dedication have made this success possible. Thank you. Once again, I thank one and all. Thank you.